Alright, so today I'm going to show you the real quick way to do the calculation of energy of EMR waves when you know the wavelength and the frequency, or the frequency. Alright, so if you've read through the section, or the pages in the section, and section 5.1, you will have seen that energy is sometimes called quantized, meaning it's composed of photons. And photons are just little tiny bundles of energy that all have basically the same wavelength moving in a line. That's what we call an EMR wave. We're going to find the energy of a photon today using the formula E equals h nu, where E is the energy of the photon, h is called Planck's constant, and it has the numerical value 6.626 times 10 to the negative 34th joule seconds. That's a joule multiplied by a second. A joule is an energy unit. And nu is just the frequency. Of the photon or wave. Now it ends up being pretty straightforward math. What I want to show you first is the units. If we're looking at energy and it's multiplying h times nu, the units for h are joules times seconds. So that's a joule times a second. The units for frequency are hertz, which if you remember is a reciprocal second. Sorry about that. So if you're multiplying a joule times a second and then dividing by a second, the seconds will cancel, and we find that our energy units then are just going to be joules, which makes the most sense. Now, as far as doing a sample problem, it's pretty easy. We have to keep in mind the same conditions apply to when we were calculating wavelength and frequency using the speed of light, c. Our frequency has to be in individual hertz. Our wavelength also has to be in individual hertz for these to work, so you have to account for the prefixes. So for example, if the frequency is 550 megahertz, what is the energy? Well, we have to go through and use the formula. Energy equals h times the frequency. So our energy then is going to equal Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And we need now the frequency in individual hertz. The prefix mega is equal to 1 times 10 to the positive 6th power. So this then becomes 550 times 10 to the 6th hertz, or reciprocal seconds. Unit-wise, our seconds are going to cancel. So our energy then, if we do the math, and we're going to use the scientific notation button again, 6.626 EE to the negative 34th times 550 EE to the 6th. And we get a pretty small number, 3.64 times 10 to the negative 25th. Does that seem like it's a wrong answer to you? Well, it isn't. It's the correct answer. The energies of these are incredibly tiny, but they're also ridiculously large numbers of them. So something like a radio wave, trillions and trillions and trillions of photons, all with the same basic frequency and all with the same energy. It's not the energy of any one that is that important, it's the collective amount of energy that makes it significant. Kind of like ants. One ant can't do a whole lot, but an entire colony of ants can do quite a bit. As far as calculating the energy from the wavelength, there are two ways to do this. Since we know that C is equal to lambda times nu, or our wavelength multiplied by our frequency, then we can also do this two different ways. If we know the wavelength, you can always use the wavelength to solve for frequency. Just rearrange this. Solve for frequency and then use it with E equals h times the frequency. But since we know these two things are the same, that's what the equal sign means, we can use the speed of light constant c and the wavelength in place of the frequency in this formula. Since E equals h times nu, we're going to substitute this in for that. So E would equal h times c all divided by lambda. And again, your Planck's constant is going to be in joule seconds, your speed of light is in meters per second, and your wavelength is going to be in just meters. If it's a prefixed value, you have to account for the prefix. So unit-wise, you'd have joules times seconds, that's your h. You'd have meters per second, which is your c, over meters. The seconds would cancel, and the meters would cancel, and you're just left with joules, which again works out well for energy. So to use this in an example, let's say the wavelength equals 375 kilometers, km. Kilo is equal to 1 times 10 to the third. So we would put this in the formula as E equals h times c over lambda, which would equal 6.626 times 10 negative 34th joule seconds. And I'm going to run out of space. I'm going to do that again on the bottom line. Equals 6.626 times 10 to the negative 34th joule seconds, multiplied by c, which is 3 times 10 to the 8th meters per second, all over 375 times 10 to the third meters. We're going to do the math then the same way, making sure we use the scientific notation button. So 6.626 times 10 to the negative 34th power times 3 times 10 to the 8th power divided by 375 times 10 to the third power, and that's going to equal 5.3 times 10 to the negative 31st. Oops. .3 times 10 to the negative 31st, and that is just joules. If you have any specific questions, feel free to ask them. You can contact me via the Remind, or you can contact me through email. Other than that, these are pretty straightforward. You have 12 problems to do on the worksheet, and you have a couple of review questions to go with the chapter. Have fun.